Our next talk is on competitively chasing convex body, and it will be given by Mark Selko.
Hi, I'm Mark. I'm going to tell you what it means to chase a convex body and how we can do that competitively. This is joint work with Sebastian Bubeck, Yintat Li, and Yuan Zhou Li. All right, so what is the problem? We're going to receive a sequence of convex sets in d-dimensional space. And right after receiving the teeth set, we have to select a point xt inside it. So maybe we're somewhere else, we get a set, we move inside it. Fine. We're going to pay a cost, which is the total distance we moved. So summed over the whole path. And we'll say we start at the origin. The question is, can we compete with an opt who sees all the sets in advance? So it's a competitive analysis problem. We'd like our cost divided by the minimum possible offline cost to be bounded by a constant that can depend on the dimension. To head off any potential confusions, let me say that we can assume our algorithms are deterministic. This is because the whole problem is convex. So if I have some randomness, I can just move to the average point over all my randomness and do better. So we can think about deterministic algorithms, and therefore we can think about adaptive adversaries, so it's all very clean. Cool. Here's an example. So we start at x0. I'm going to use red points for the online and blue points for the offline. So on this first request, we don't really know why opt is going straight. Okay, we still don't know. Now we see. And so you can see that the red point moved a little bit more than the blue point, but maybe it's not so bad. Okay, so now I want to run through a couple of motivating stories for why this problem is connected to other problems. And the first one is chasing convex functions. The story here is that we can, instead of sets, we can receive cost functions. So we're going to receive positive convex cost functions, and we're going to pick xt after seeing ft, and we're going to pay the same movement cost, but we're going to pay ft of xt. So ft is like requiring our point to be in the set. Again, the aim is to be competitive, and these are actually equivalent. So it's pretty easy to view a convex set as a convex function. You can just take the function which is 0 on the set and grows fast away from the set, or is even infinity off the set. To reduce the other way, you can go up one dimension and take a function on d dimensions and look at the set, which is the region above the graph. This is a convex function, and it's pretty easy to get a reduction up to a constant factor. So these problems are equivalent. Okay, so we can also try to fit this problem into a more general framework. You might notice it looks like something like K-server, but it's sort of convex, whereas K-server is more of a combinatorially complicated question. And there's this general viewpoint called metrical task systems, which includes chasing convex bodies, K-server, and chasing convex functions. In metrical task systems, we have the same goal of getting a finite competitive ratio with movement and function cost, but we allow kind of an arbitrary metric space and some arbitrary set of cost functions each round. Okay, so if we allow an arbitrary cost functions on a worst case endpoint metric space, the competitive ratio is something like log n. And for us, n is infinite. RD certainly has infinitely many points. So we can hope that the convexity will help us and kind of make the competitive ratio finite anyway. And this is the case for K-server. You can do K-server on an infinite metric space and get a finite competitive ratio only depending on K. Okay, another motivation, which is a little different, is online convex optimization. So let's say that the functions are Lipschitz. Then the movement cost we can think of as an upper bound for the advantage we got in getting to see the cost function before picking the input. Right? We could also think that we pick the input point and then we see the cost function. And this seems like a harder problem, but if the functions are Lipschitz, then we can just put this down as the movement cost. Now, if we see the cost function after we pick our point, this looks like online convex optimization, and there's lots of work on problems like this where we aim for a regret bound instead of a competitive analysis bound. So here we're comparing against a benchmark which is the best single input point. And we want to say the regret is something like square root of t, or something little o of t. If we want to compare against a changing benchmark, we can't hope for regret bound, and we also have to penalize the movement of opt somehow, so chasing convex functions becomes a kind of natural formulation of the problem. Okay, so what was known before? So in 1993, Friedman and Lineal introduced the problem. They gave a square root d lower bound, which is pretty straightforward, and they gave a competitive algorithm in 2 dimensions, which is already not especially easy, but it's not so bad. Okay, and there wasn't much progress, and people started studying restricted cases where you could prove things. I'll mention a couple. So it was shown that if all the bodies are affine subspaces, then you can be competitive. And on the function side, people showed that you could be competitive for restricted classes of convex functions. Okay. There's also another restricted case of the problem called nested convex bodies, which has proved very helpful in understanding the full problem. So I'll say a little bit about that. This is the restricted case where the bodies are shrinking, they're nested. So you start with the biggest one and then you shrink down. And it becomes an easier problem. So you can actually show greedy is competitive here, which is very not true in the full problem. This is actually kind of neat. Greedy here amounts to, analyzing greedy amounts to thinking how far can gradient descent go? Like how far can the path of gradient descent go if you stay in a unit ball? And recently, it's become pretty well understood. So a paper by the same set of 4 authors as the one I'm talking about now gives a nearly optimal O tilde of root D algorithm. And yeah, so it's pretty well understood. Okay, so our result is the first finite competitive ratio for the full problem, which is exponential in the dimension. I should say that there was a big improvement just last month due to myself and Argu, Gupta, Guruganesh, and Tang from CMU, which is a linear bound in any norm and nearly tight in Euclidean. So, well, okay. Let me say briefly what goes on in this work. It's kind of a different strategy. So to get this linear upper bound, you consider the work function, which is kind of encoding the cost for opt to end up at some position after any requests. And you stay at the Steiner point of this function. The Steiner point has 2 definitions, which are equivalent by the divergence theorem from multivariable calculus. And it's kind of miraculous. So one of the definitions controls the movement cost, and the other ensures that you're in the set. I really think this is magic. The proof I'm going to tell you about today is not magic, so they're probably going to generalize differently. Also, as I'll say at the end, the Steiner point algorithm is not state-of-the-art for the nested case. The state-of-the-art for nested case is more similar to this one, so it's possible that this one will take the lead or they can be combined or something. Okay, so let's get into the proof. So I mentioned that greedy fails. Let's try to see why this is. Let's just say every set is a line and we're in 2-dimensional space. Why does greedy fail? Well, it fails if the lines rotate slowly about a center point, because alg, as depicted here, will keep moving basically in a circle. In the kind of continuum limit, it will move in a circle. And opt should just move to the center and only move a constant amount. So we don't want to do this for sure. How can we do better? We can move towards opt. So for chasing lines, this has a pretty simple description. We are going to move to the closest point on the next request, and then we're going to move just a little bit towards the place where the new line and the previous line intersect. Okay, so why is this good? Well, basically, if opt is further away, so on the left of this picture, from the intersection point, then it also moves a lot, so we're happy. And if opt is closer to this intersection point, then we move closer to opt. So we can use the distance of our online point alg to the offline point opt as a potential function and a pretty straightforward analysis shows that we are competitive. So, okay, we'd like to do this in general. And our strategy is to split the time steps into phases and ensure that we make progress in each phase with respect to some potential. The potential is going to be essentially the distance to opt, but it'll have like another bell or whistle in it. But you can just think of the distance to opt. So we're going to define opt set to be basically the set of points we're trying to move closer to. So opt set is defined within a phase, and it's all the possible positions for an opt that moves only a small amount within the current phase. So this will shrink over time as the phase goes on, and at the end of the phase, we'd like to be closer to every point in opt set. Then we can finish with a similar potential argument because either opt didn't move very much, and then it's an opt set and we move closer, or it moved a lot and then we're also happy. Great. And a key observation, similar to this observation that randomization doesn't help us, opt set is convex because we can average short paths and get another short path. And if we have a convex set, we can move towards the convex set, so maybe this is a reasonable thing to hope for. Okay, but there's a problem, and let me just give you the quick version right now. Let's say opt set is a really long line, then there are points that are far away on each side, and we can't really move much closer to both of them. We can move closer to the line, but if we move like epsilon, we're probably moving something more like epsilon squared closer to these faraway points by the Pythagorean theorem. So that's bad. And it's maybe not so clear what we could do here. We can't, if we pick left or right, we're not going to do what we want. So what we need to try to do is procrastinate and just not move very much at all until opt set really shrinks in one of these long dimensions and we can really do something. Okay, that was a preview, so now let me kind of get down to what the algorithm is actually doing. So first of all, we're going to choose a scale little r for each phase. And during the phase, we're going to work inside a ball B with radius big R, which is some polynomial in the dimension times little r. So it's a big ball, kind of, which captures what we're doing right now. So we're going to look at opt set, which is the set of endpoints of paths with movement at most r, and which stay inside this big ball B. Opt set is just the ending points of these paths. When opt set has small diameter, we're going to do some sort of updating step, and we'll say that we made progress. Okay, so there are two ways we can make progress. On the left picture, opt set is small, and it's contained deep inside the ball, and then we can shrink the ball around it, and with this appropriate potential I've written down that you don't need to worry about too much, somehow we make progress. Basically, we're moving closer. Even though we're not literally moving closer to every point, maybe we're moving closer because we zoomed in more. The other case is that opt set is right on the edge of the ball, and then we're scared because we were only looking at the inside of this ball. So if opt set is right on the edge, then maybe there are low movement opts that are outside the ball, really far away, we haven't been keeping track of. So if that happens, we're going to grow the ball and start a new phase. And we can actually set up the potential so that both of these are good outcomes. Okay, so what's left to do is to ensure that until opt set shrinks, we have small movement in our online algorithm. If we have movement O of r, then we'll get the same competitive ratio up to this poly d factor for big R versus little r, essentially. So the remaining goal is to ensure that we can move O of r as long as the phase is still going. So there's kind of a thing you can first try, which I'm going to call the easy case. And here the first observation is that if we have any request during the phase, opt set has to be contained in an R neighborhood of it, just because you have to move into the body and then you can't move more than R at all. So if we have multiple requests, then we get this intersection, which is in blue over here. So what we can try to do is we can stay near the center of mass of opt set, which is this big oval here. And let's say we get a request that actually forces us to move. Then we're going to get some cutting plane and it's going to be within distance r of the center of gravity, and we're going to remove everything on the opposite side from offset. This is just because if we have an r neighborhood of this convex set kt not containing the center of gravity, we get a cutting plane. And if offset is long compared to r in all directions, then we're essentially cutting through the center of mass, and we reduce the volume by a constant factor. This is called Grunbaum's inequality, or approximate Grunbaum. So in poly d iterations, certainly offset should shrink a lot, and we could hope that eventually we get small diameter, and then we can say that we've ended the phase and we haven't moved too much. Okay, this doesn't work because offset could be really long in some directions and short in others, and we could just keep cutting in the short directions like this. So that's bad, and we don't make progress. Okay, so basically the idea is we're going to break up offset as long directions and short directions and kind of separate them. We can always do this because it's convex, and for example, you can approximate a convex set with an ellipsoid, and an ellipsoid has well-defined set of directions. So you can always do something like this. And we're going to only move in the short directions. We're just going to stay at something like the center of mass in the long directional set, and we're going to only move in the short directions. We're just going to wait until the long directions shrink. Why is this competitive? This is kind of the heart of the argument, and the reason is that we can stay competitive among algorithms that remain in the short subspace by an induction, and we can take a kind of dynamic moving average. So we can take far away ops in the long directions and take a time-varying moving average, which stays exactly in this short subspace we're in. And this is going to show that there's some competitive algorithm that stays in the short subspace. So as long as we are competitive within the short subspace, we're kind of happy. Okay, this is the main difficulty in the proof, and this is why we have exponential dependence in this algorithm. Okay, here's a quick slide showing the final algorithm. So it's really, at a high level, it's not so complicated. And here's a quick look at a potential analysis. There's just a couple of cases, and they all just kind of work with this not so complicated potential function. Okay, to conclude, we gave the first finite competitive ratio for chasing convex bodies. And last month, there was an improvement. So a question that is still open is, can we achieve a nearly optimal competitive ratio, which is probably going to distinguish different norms. So in this paper on the nested case, we gave an algorithm that was kind of a similar recursive algorithm to the one I just explained. And it can be made nearly optimal in any LP space. And the Steiner point, which gives the linear competitive ratio for the full chasing convex bodies problem, has a polynomial gap unless you're in L infinity. So we could hope to maybe even combine these approaches and refine the competitive ratio to depend on the norm. Another fascinating problem is, can we give a general theory of metrical task systems that explains chasing convex bodies, K-servers, and maybe a lot of other problems? Thank you. So you can, if you have half spaces only, it's just as hard as the full problem because you can write any convex body as an intersection of half spaces. So ellipsoids or balls is just as hard. Lines are O of 1 competitive dimension independent. So that's something. Yeah.
One more question. What about the other metrics? What other differences L1, L2?
Yeah, so the question is, what about other norms?
Yeah,
right? Yeah, so for what I just described, it's the same because any norm is equivalent to a Euclidean norm up to a root d distortion factor. So, 2 to the O of d times root d. So great, 2 to the O of d. Yeah, and like I said, it's interesting to try to get the exact power of d depending on the norm. Right now, the state of the art is a linear bound d for any norm, but it doesn't distinguish between them, and they're likely different.